In this segment, we'll pick up where we left off with the call of max on line 37 of prog5.s. I'm also going to move this stack frame we had for max of 3 down a little ways, since we'll be building on top of that and labeling it appropriately. So you now know enough to figure out most of function max, which starts up here on line 7, most of function max on your own, with the probable exception of lines 15 and 16, which we'll talk about. It starts by setting up a stack frame, though its stack frame differs a bit from that of max of 3. And question 1. There is one notable omission in max's stack frame versus max of 3's stack frame. What is it, and why is this omission okay in max's case? Note, by the way, that a BX instruction, as on line 21 down here, branches to a location held in whatever address register is given it as an argument. So with that information, you should come up with the answer that the difference is it doesn't save the LR on the runtime stack. Instead, it leaves LR unchanged throughout the function call. There's no modification to it, and no other functions are called, and so it uses it directly to jump back to the end on line 21 here. Okay, since we're looking at line 21, just by the way, can you rewrite it to do the same thing but with a different instruction? Well, there are a couple possibilities, but the obvious one would be to write it as move PC, LR, move the LR into the PC, and it would accomplish the same thing. The BX instruction is a relatively recent addition to the ARM ISA, and it's slightly faster on newer processors than a move, and so it's preferred. And so, question 3. How many words of local state does max's stack frame have? And what is in each word in ascending order within the RTS or in descending memory order? You can use names from the C code to describe the contents. And the answer is that there are 2 words, which is why line 9 subtracts 8 bytes from SP. And in ascending stack order, not memory order, there are parameters X stored on line 10 and Y stored on line 11. And I'll draw the max stack frame in the diagram now. So I've moved FP and SP up, and you can see that the old FP store here is pointing back to where FP used to be at the bottom of the prior stack frame. Okay, so question 4. What part of the C code for max is implemented by lines 12 through 14? It's just one part of an expression. It's not a whole C statement. The answer is that those 2, or those 3 lines I should say, load X and Y into R2 and R3, and then they compare them. So they're doing the X greater than Y comparison in the return expression. And so we come to lines 15 and 16, which need some explanation. You already know that the results of a CMP can be used to control a branch operation in the next instruction. For instance, BGT will branch if the result of the preceding compare was greater than. But the result of a CMP can be used in more powerful ways. First, any instruction may be made conditional on the result of the CMP by adding the correct 2 letters to the opcode. So move GE means move only if the CMP result was greater than or equal to. And for, say, a different example, an add LT would mean add only if the CMP result was less than. The second point is that a CMP result stays around for more than just the next instruction. Any instruction after a CMP, even several steps later, can still use that result. The result stays until replaced. For now, the only way we can replace it is another CMP. We'll see other ways later. So that means that that result is still available on line 16. You now know enough to decipher what lines 15 and 16 are up to. What do they do? And tie it back to the C code. And the answer is that they move either R2 or R3 into R1, whichever is larger, because only one of the two will be performed. The first if the result was a greater than or equal to, for R2 being larger, and the second if the result was a less than, meaning R3 was larger. And this then completes the implementation of the x greater than y, then x else y expression in the C code. And then question 6. Why is it necessary to move that result we just computed from R1 to R0 here on line 17? Think about what the C code does with the result of the expression. The answer is the result is the return value of the function, which must be put into R0 as previously discussed. It's part of the calling convention. So then, lines 12 through 17, all together, implement return x is greater than y, then x else y. Now, you may also be thinking that they do so very inefficiently, and you'd be right. Compilers produce dumb but accurate assembly code, unless you ask them to optimize. And we'll do that in a later module, but then we'll find that compilers produce very smart but hard to understand assembly code, filled with interesting efficiency tricks. It's a great way to learn about compilers and ARM architecture, but it's a poor way to learn assembly code at first. So we'll stick with the slightly dumb and unoptimized compiler-generated code. However, even this assembly code has one nice optimization, and that's lines 15 and 16. Now, the same job could have been done with a couple of branches, right? So first, just to see that, write a replacement of lines 15 and 16 using branches and simple move instructions. You will need to add 2 labels. So here's one possible answer at least. And you can see what it's going to do is the same CMP, and then if it's greater than or equal to, we'll branch to R2 is bigger and do a move of R2 into R1 at that label, and otherwise we'll fall through and move R3 into R1 and then branch around the other alternative to all done. Now, that's a good bit longer, but even worse, it has a couple of branches. As we mentioned earlier when explaining why the compiler puts while loop tests after the loop body, branches will slow down a RISC processor. We'll see why in a later module, but for now we can appreciate the elegance of lines 15 and 16 in avoiding any branches. Okay, so to wrap up, please explain why lines 19 through 21 tear down the current stack frame, how they do that, and how they return to the caller. And then specifically, could we replace, just as a thought question here, the LDR FP SP #4 with just LDR FP SP without the #4? Would that be okay? Okay, so line 19 moves the stack frame pointer down to match the FP, which removes the local state from the frame and returns SP down to the bottom of the frame. Line 20 loads the old FP value back into FP and moves the SP forward in memory to eliminate the last word in the current frame. So that #4 addition is actually essential and could not be omitted. And we'll put it back there. The caller expects SP to be left just as it was when max was called. Now, I'm sorry, I should also have moved FP down to the point where the old FP was because of that move instruction. So as you can see, it's just the way it was before. And then finally, line 21, as we already discussed, returns to the caller with the result already put in register 0. In the next segment here, we'll look at main in this program.